In this section, I'm going to talk about the various power generation methods and also the advantages and disadvantages of each. So in here, these are kind of the main types. I'm not going to talk about gas because that's kind of been discussed in other lectures, particularly when we talked about the Rankine cycle. But I'm going to talk about each of these in turns. I'm going to talk about coal, nuclear, fission, tidal energy, wind energy, solar energy. And I'm only going to give a very brief introduction to these technologies, as these are covered in more depth in the energy technologies modules, which you can take in your third year. So I'm just going to start off with this. So this shows the energy density versus specific energy for different fuels. And I used a similar plot when we were looking at how various different energy sources stack up against diesel and gasoline when looking at hybrids. And basically, you want to be in the top right-hand corner. So you can see natural gas, all the hydrocarbons, oil, gas, and natural gas, are kind of down in the bottom left-hand corner. But when you consider nuclear power, then it's kind of bit unavoidable in the fact that it has such a high energy density and such a high specific energy that it does make it very good fuel. I mean, I'm not saying it's perfect. Obviously, it has some very major drawbacks, but in terms of an energy source, if you're looking at purely from an engineering point of view, then it's a very good fuel to use compared to some of the other hydrocarbons, which don't give you, haven't got as much higher energy density, and don't have such a high specific energy. Okay, so how does a coal-fired plant work? Well, the coal isn't just shoveled in, as you perhaps might have thought. In fact, it's much more complex than that. The coal is taken from the heap, passed along conveyors, and this can be stored outside. If you remember, I mentioned this in one of the previous lectures. It doesn't matter if it gets wet. The reason for that will become clear in a minute. Because before the coal enters the boiler, basically it's pulverized. It's ground down to very fine powder. Then it's kind of heated on the way to the boiler, so any moisture that was in the coal from it being stored outside is driven off, and then enters the boiler. And you can see here's a picture of a burner in a coal-fired power plant. So you can see it's really kind of injected and very, very finely to create this quite impressive flame here. There is a problem with ash, the kind of the residual of the combustion process, so that needs to be collected, and that's kind of one of the main drawbacks, apart from the emissions of this process. The ash is then either collected and disposed in landfill, or some of it can and some of it is recycled into building products, so put into various aggregates that can be used in the construction industry. So I kind of mention this because talking about coal-fired plants, so they're not, as I say, they're reducing in popularity in the UK. I mean, we're starting to switch from coal, but a lot of other nations are still reliant on coal, such as the US, to generate a lot of their power. Okay, nuclear fission. So nuclear fission, I should perhaps say from the start, is quite a kind of a Marmite technology, in that you kind of love it or hate it. Really, it tends to be quite divisive in that respect. People think it's very good, or you think it's bad, I should say, actually. So the reason I say that is because obviously you've got your own opinion about that, but it can be quite divisive. But how does it work? So essentially works like this. So you take a nuclear fuel, and basically that the energy is released is when the nucleus of an atom splits into smaller parts. So it uses a neutron to basically is fired into an atom nucleus. That causes it to split, which releases more neutrons, which then go on to split other atoms and so on and so on. And it's this process here, this energy that was binding this large nucleus together, which is released when it splits into these smaller ones, and it can create, huge amount of energy. Now, the way that this is kind of controlled is that, as you can see, this is the schematic of the reactor. So coolant's passed in, it gets heated out, and is what is used to generate the steam. So you can either generate the steam directly, or you can use a pressurized plant and a heat exchanger to then generate the steam from that. You have a moderator block, which basically slows down the neutrons, and then also you can raise and lower these control rods, and basically these are the ones that absorb the neutrons and control the rate of fusion. So the moderator block just purely slows them down to a level where we can control them with the control rods. And as I said, the heat is then generated to the coolant, which can be used to generate steam, either directly or with a pressurized water reactor. So the advantage of this is clean in that during the process you're not releasing any emissions. So you're not releasing any carbon dioxide into the atmosphere or NOx, etc., etc. Because of the amount of energy that you have available, it can provide a very high baseload, which is good from an infrastructure point of view. Because if you think that you want a large proportion of your energy mix to come from a very stable energy source, so that if there's any fluctuations, you know that you can deal with that. And when they're running, they have pretty low operating costs. However, it does have some major disadvantages, I'm sure you're probably aware. Nuclear waste is obviously the biggest disadvantage of this. What do we do with the waste once we've spent the fuel in reactor? Currently, we don't really have an answer for that. It's stored in special storage facilities. There are some technology in France where you can use breeder reactors to use some of the waste nuclear fuel. But yeah, that's quite a big and common problem with these types of reactors. Second disadvantage is that when it goes wrong, it goes very wrong, and I won't talk about them here, but there have been some very high-profile disasters such as Chernobyl, which have resulted in a large loss of life due to the failure of these reactors. And also, they do actually have quite initial high construction costs to put them together. But notice one thing I haven't said here about the disadvantage is the radiation from a plant that's operating normal. And the reason for that is it's not actually a problem when it's running. And just to illustrate this, I've got some information here for you. So the SIVERT is the SI unit for ionizing radiation doses. Okay, and a banana contains naturally occurring radioactive isotopes, potassium-40 in fact. And so basically one banana has equivalent to 0.1 microSieverts. So this has led to what's called the banana equivalent dose. So if you convert these kind of sieverts into equivalent bananas, then you get the same dose living within 50 miles of a nuclear power station as you do from one banana. You get the yearly dose living within 50 miles of a coal power station is equivalent to 3 bananas, and so on and so on. And it'd take you the equivalent of 100 million bananas to kill you. So, but the point here is that if you look at the dosage from this is a bit tongue in cheek, obviously, but on a serious point, the radiation, the yearly radiation from living within 50 miles of a nuclear power station is far less than the dose you would get. Is less than the dose you get living to equivalent coal power station, from your average daily background dose, or even from a flight from London to New York. So the radiation from these plants is not a problem under normal operation. Okay, so I'm going to talk about tidal energy now. Um, Tidal Energy in the UK has a huge potential, actually. One of the biggest potential in Europe, actually, according to some reports. And this is because of the high tide range that we have, in a range of 7 to 9 meters, which makes it, ideal for this type of technology. So, how does it work? Well, basically, you build a barrage or a dam, usually across an estuary. And what you do is basically the sluice gates are normally open, and as you get high tide, it fills up the tidal basin. And when you get to high tide, you close the two sluice gates, and basically trap the water in the basin. And then you wait till the ocean on the other side is approaching low tide, and now you can see you've got a head difference. You've got a difference in between the water that you trapped in your basin and the low tide height on the other side of the gate. And when you approach this stage, you can then lift up the gates on the barrage, and basically, obviously, the water will flow out of the basin back into the ocean. And as it does that, you can use the potential energy, which is converted into kinetic energy, to drive a turbine to generate electricity. And once you've built the barrage, this is a good way to generate it. It's very predictable. It's relatively cheap, as I say, once it's been built, and a nice, relatively good, clean way of generating electricity. And in the UK, we're looking at there's a potential site just outside Swansea. So this is showing a map of Swansea Bay. So you've got Swansea City there, and then you can see this is the potential basin for what's going to be called a tidal lagoon. So as I said, it's normally across an estuary, but you can obviously make a lagoon using the land on one side to trap it. And this is aimed for construction in 2008, although at the time of recording this, there was no decision that had been made on this. As you can see, there's a very significant upfront cost with this. It's going to cost, or predicted to cost, I should say, £1.3 billion to do this. But once it is constructed, it'll generate enough power for over 150,000 homes and have a lifespan of 120 years. So it'll give you a lot of clean, cheap energy for quite a long time afterwards. However, as with anything, there are several disadvantages. The main one being the impact on the local wildlife that this will have, and also the impact on the wider tidal system. Because as you can imagine, there's a natural kind of ecosystem and tidal system here, and then you go and build a barrage in a way, you're bound to impact that in some way. But as I say, the designers and the engineers and the ecologists will obviously have that in mind and try and minimise that as much as possible. Wind energy is also another kind of growth area, if I can phrase it like that the UK is looking at to kind of exploit its natural resources, not just in terms of tidal, but also in terms of wind. And the UK has one of the best conditions in Europe for wind power. And basically, what a wind turbine does is the same way that we've been talking about turbines throughout this module. It extracts kinetic energy from the wind and turns it into electricity by turning a generator with the blades. And there's currently around 6,000 wind turbines in the UK with a combined capacity of 12 gigawatts. Three-bladed turbines tend to be the preferred option. This because it balances the forces on the on the device as an overall. However, the main disadvantage with wind turbines is that they're little unpredictable. Because obviously, if you've got no wind, you have no energy, and that can be a problem. If it's not very windy on FA Cup final day, then your supply and demand you might not have enough supply to meet your demand. So that is one of the big disadvantages of wind energy. Another kind of not disadvantage but matter for debate is where to site them, because you can site them onshore, in plains and kind of in highlands and that kind of thing, or you can mount them offshore, and each kind of have their pros and cons. So let's look at these in terms. So in terms of the predictability of wind speed, the predictability is better offshore. We can the meteorologists can better predict the wind speeds offshore than they can onshore, and also the wind direction, so that gives an advantage to offshore. In terms of the connection to the grid and installation, common sense would tell you that it's easier to install and connect to the grid onshore wind turbines than offshore, because obviously there's a lot of challenges associated with that. You need to float all the turbines out on barges, lay the foundations, etc., etc. NIMBY, or not in my backyard, is obviously another advantage. To some, or probably most people I should say, the idea of having a wind turbine within the vicinity of their home is unappealing, mainly because people call them eyesores, but also more about the public perception of the noise that they generate and the vibrations that they generate or may generate. So obviously you don't have that problem if you mount them offshore, because no one can see them. They're out of sight and out of mind. And also in terms of environmental impact, you could argue that mounting them offshore is less of an issue to that. You're not destroying homes onshore. Okay, might destroy a little bit of marine habitat, but the impact isn't as great as mounting them onshore. And lastly, but not leastly, solar power. So our sun is a source of an immense energy that's radiated in all directions, and obviously some of it comes towards us. But obviously, because of the curvature of the Earth, countries nearer the equator receive the highest energy flux, and you can just do a simple sketch to prove that to yourself. That said, the EU as a whole produces more solar power than anywhere else. And there's two main ways that you can harness power from the sun. There's photovoltaics, where you're actually taking the photons from the sun's rays and using that in a special substrate, so that when the photons land on it, they basically generate a differential in a current actually across the device. Or the other way of using it is to take the sun's rays and basically use as a heat source, so focus the sun's rays onto a heat exchanger, which is carrying a fluid, a working fluid, which you can then run through Rankine cycle, etc., or some sort of thermodynamic cycle to generate power. So there's two ways you do it. You can either use the sun's rays directly to generate electricity from it, or you can transfer that energy into a working fluid, which you can then operate in a cycle to generate electricity. So the main advantage is obviously it's free, but there's a couple of main disadvantages in that it requires a lot of space, and obviously it is weather dependent. Not much you can do if the cloud comes over when you're trying to generate electricity.